In this lecture, we will see introduction to error control codes and the role they play in digital communication systems. We will use a very simple model and describe the role and provide one or two simple examples of coding situations and show what happens there. Okay, so that's the basic objective of this lecture. So let's begin. Okay, so here's a brief outline. We will start by talking about digital communication system models. In particular, we will talk about the modulation scheme which is called BPSK, and then we will describe how to think of bit error rate versus signal to noise ratio. Now, this is the fundamental trade-off in most digital communication systems. We will talk about that for a little while. And then we will introduce how error control coding or error correction coding works in a digital communication system. We will specifically talk about a plot of bit error rate versus normalized SNR or EB over N naught in the presence of an error control code in a digital communication system. And then finally, I will conclude with how encoding and decoding is typically implemented and provide simple examples. Basically, the repetition code is the example we will use. Okay, so this is a picture of what is called an AWGN channel, additive white Gaussian noise channel, and the use of modulation over such a channel. So, we do not have the time in this course to go into details of how this picture comes about, but I will start with this as an assumption, and I will assume you have familiarity with digital communication to know what I am talking about. Okay, so as you know, mostly the communication medium is will transmit signals, electrical signals, and in a digital communication system, one needs to transmit bits. Bits could be 0 or 1, and how this is done is usually the bits are converted into a signal. Okay, so that's what is called modulation. That's what's there on the first block here. Modulation refers to converting bits into signals. Okay, and once the signal is ready, it is sent across the channel, and for our purposes we will assume that what the channel does overall is to add a noise signal, which is additive in the sense it adds, which is also white in the sense it is sort of independent from time to time, and it is Gaussian distributed. So, this is additive white Gaussian noise model. The noise signal n of t, this is the noise signal here, it adds to the signal, transmitted signal, to obtain a received signal r of t. Okay. So, you get a received signal r of t, and this is usually filtered and sampled. Okay. So, there is a receive filter and sampler here, and usually one can design this so that you do not lose any information and you get samples. Okay. So, as it turns out, one can make a direct connection between the bit that was transmitted A and the sample R that was obtained. Okay. So, this is the theory of how you model a digital communication system in the discrete time domain, and once you do that, you can make a decision to get A hat. Okay. So, this is sort of crucial. So, R, the received sample is the information about all that you did in the digital communication system after you have filtered. Okay. So, all the information about A is in R. Okay, and you can do a decision. So, let us look at this in the discrete time domain. We had the continuous time domain in the previous slide. This is the discrete time domain. You can see I have gotten rid of the variable t. Okay. So, what people usually do is to represent the transmitted signal s of t in terms of a symbol. Okay. So, this is done using a basis representation and all that. This is quite standard. We are not going to look at it in detail in this class, but let us assume we do that. Okay. So, this modulation converts the bit A into a symbol S. Okay. So, this is called the symbol. It is quite important to know how this works. Okay. And instead of a noise signal n of t adding to the signal S of t, we can have a discrete version of the noise. Okay. So, you have a discrete noise version, and like mentioned here, it is Gaussian distributed and it is independent from symbol to symbol. Okay. So, these are things that you can prove by carefully looking at the model. Okay. So, at the end of the day, we have a really simple model for the entire digital communication process. You have a bit, you convert it into a symbol S, and it's sent through a channel, whatever happens to it, all that you are concerned about is this received value R, and that received value R is simply the transmitted symbol S plus a Gaussian distributed noise which is independent from symbol to symbol. Okay. So, this is a very simple and elegant model for a physical complicated system, and it's quite important, and because of such models we are able to do advanced theoretical studies of these systems and improve them very nicely. Okay. So, once you have this value R, you can run a decision device and come up with an estimate of the symbol. This is the estimated symbol. Okay. Once you have an estimated symbol at the receiver, you can do a demapping and go back to the bit. Okay. So, this is the estimated bit. Okay. So, this is the model that we will use throughout this course for capturing the behavior of a digital communication system. We will not go into any other details than this. This is the model that we will use. Okay. So, there are assumptions here on how we assume the system has to work, the timing has to be right, all of that we assume, yes, that is true, but those are engineering problems that we will not focus on in this class. We will work with this model and try to see how to get the best out of this model. What is the best performance that one can extract from such a system. Okay. So, that is going to be the goal of this class at least. Okay. So, what are the various modulation schemes that are used in practice today? Okay. So, like I said, you have a bit or maybe a few bits. A few could be 2, 3, 4, 5, 6. Today people use even 10 bits sometimes for doing modulation, and you take these bits and convert them into a symbol. Now, the symbol is typically can be complex valued. Okay. So, how do complex values convert to a actual transmitted signal S of t which is real? That is again theory that we will not see, but one can assume that the symbol is complex valued. This is the idea of QAM, quadrature amplitude modulation, which maybe you are familiar with. Okay. So, I have shown here 3 pictures. The first one is BPSK. I am underlining this because this is the only modulation that we will use in this class. But I want to point out there are other more advanced modulation schemes like 4QAM, 16QAM, which are actually used today in communication systems. We will not talk about them in this class. We will focus solely on BPSK. So, how does BPSK work? Bit 0 is mapped to the symbol +1, okay, and bit 1 is mapped to the symbol -1. Okay. So, that is it, that is BPSK. Like I said, there are more advanced modulation schemes which actually use complex values. We are not going to focus on those kind of schemes here. We will only use BPSK over AWGN. Okay. So, that is the system we are going to study next. Okay. So, let us look at BPSK over AWGN. It is important to know how this system sort of works and go through it with an example and imagine what is going to happen, because this is the model we will use throughout this class. Till the end of this class, we will use the same model. Okay. So, you have bits coming in from the left hand side, these are bits. What I have shown here is a typical example. Okay. So, this is a typical example here. Of what can happen. So, I have shown here a bit sequence A which is 0 0 1 0 1 1 0 1 1 0 1. This could be a bit sequence that you are sending through your system. Okay. So, the first step is you map the bit into a symbol. Okay. Now, for this particular sequence, how are you going to do? You are going to do a BPSK mapper. So, 0 goes to +1, 0 goes to +1, 1 goes to -1, 0 goes to +1, so on. Okay. So, that is what happens, all right. And then noise gets added, okay, and you get received values. Okay, noise gets added and you get received values, and I have shown a typical possibility for a received value here. I am showing only one decimal place. It could actually be more than one decimal place depending on how much resolution you have in the system. Here is an example. So, the symbol +1 was transmitted, it got received as 0.8, which means what? The noise was -0.2. Okay. It was Gaussian noise, it can be positive, negative, typically you think of noise as being small. Okay. So, the noise could have been minus 0.2 and you got 0.8 at the received value. The second symbol is plus 1, the noise was minus 0.8 this time. So, you got 0.2. The third symbol was minus 1, the noise was plus 0.2 at this time, you got minus 0.8, so on and so forth. Okay. So, you go through and you send all the symbols. Some noise happened, you can't predict the noise, you do not know what noise it will be ahead of time. So, even if you send the same symbol vector again, you will not get the same received value, right. So, you will get some other received value, and that is in essence the problem in digital communication. How do you work against that noise? Okay. So, what do you do after with the received value? Okay. So, if you think about what is going on, so here is an axis. Okay. So, here is 0, here is plus 1, your symbol corresponding to bit 0, and here is minus 1. Okay. You are transmitting either plus 1 or minus 1, and noise gets added, and your received values are going to be maybe here, 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 maybe, right. Most of the received values maybe will be here. Okay. But a few received values can also be here. Okay. So, this x indicates received values. Okay. So, at the receiver you get only these red values, okay, all over the place, 0.1, 0.2, minus 0.2, minus 0.3, minus 0.5, like that you will be getting. Now, you have to decide for every received value what would have been the symbol that was transmitted. Okay. So, that is the decision you have to make. Okay. You have to look at the received value and decide, was the transmitted symbol plus 1 or was the transmitted symbol minus 1. Okay. Now, remember the noise is Gaussian, it is symmetric and all that, it has very easy description. So, one very obvious thing to do is to draw a threshold at 0. Okay. What do I mean by threshold at 0? Any received value to the right, I will decide is a transmit is any received value to the right of 0 or any received value which is positive, I will decide for that received value the transmitted symbol to be plus 1. Okay. So, that is the thresholding at 0. If the received value is negative, it is to the left of 0, then I will decide that the transmitted symbol was minus 1. Okay. So, that is my decision. I am going to use this simple thresholding rule to decide whether it was plus 1 or minus 1. Okay. So, on this side S hat, which is the estimate of the transmitted symbol at the receiver, is plus 1, and on the left side S hat is minus 1. Okay. Now, I want to point out one very important thing. Okay. So, this thresholding can cause error. Why is that? So, let us take a typical, let us take a received value which is close to 0. Let us say this one is 0.1, let us say. Okay. If you have a received value of 0.1, the transmitted symbol could have been plus 1 and the noise could have been minus 0.9. Okay. Or the transmitted symbol could have been minus 1 and the noise could have been plus 1.1. Okay. And there is no way at the receiver that you can know which of these things happened, right. You do not know, both of these could happen. Now, you are looking at the noise value and you are saying, okay, 0.9 is smaller in magnitude than 1.1. So, it is more likely that the noise of 0.9 happened than that the noise of 1.1 happened, and you are deciding that you are going to go to plus 1. That is a choice that you make, and that choice can be erroneous. Okay. It can be wrong. Okay. So, it can happen that the noise was actually very bad and you were not in luck and noise was actually 1.1 and it was actually minus 1. In those kind of cases, you will make an error. Okay. So, error can happen, that is something to remember. It is all right. Okay. So, any thresholding you do, error can happen. So, the question is, can we characterize the error, can we find the probability of error. Okay. So, here what I have done after the received values I received is, this is a thresholding at 0. Okay. And here I have estimated symbol. okay, and this is estimated bit. Okay. So, you can see what I have done here. Whenever the received value is positive, I am estimating it as plus 1. Whenever the received value is negative, I am estimating it as minus 1. Okay. So, that is what happens here. Okay. And once you have the estimated symbol, going to the estimated bit is very easy. You see, if the symbol is plus 1, you say it is 0. If the symbol is minus 1, you say it is 1. That is it. Okay. So, the last part is quite easy because you went from 0 to plus 1. From plus 1, you go to 0, right. So, that is what you do, and other way also, 1 you go to minus 1. So, from minus 1 you go back to 1. Okay. So, that is what you are doing here in the last part. Okay. So, now what are these two things? Okay. In these two instances of transmission, there was an error. Okay. So, notice what has happened. You transmitted a bit 1, it gave you the symbol minus 1, and then the noise was so high, the noise was plus 1.2, that you went to the other side of 0, okay, 0.2, and your thresholding device has no other way than to conclude from 0.2 to plus 1, and from there you made an error. Okay. So, let us look at this other case. You transmitted a bit 1 again, it was minus 1, the noise was so high, it was 1.1, it went off to the other side of 0 and you made an error. Okay. So, like I said, you can make an error, but it turns out you cannot do anything better in this scenario. So, this thresholding at 0 is an optimal way to design. Okay. Optimal in the sense that it produces the lowest probability of error on average. Okay. So, that is something we can prove. We will not look at the proof in this course, but this is what you can do. Okay. So, once again, the idea behind the slide is to show you what happens in a BPSK AWGN system, and this is a good understanding that you should have. So, depending on the noise values, you can make errors, but this is the best way to operate in BPSK AWGN. Okay. So, now the question is, can you do anything better? Can you improve on the error rate and all that? So, that is what error control codes bring in. We will look at that as we go along.